Billions of liters of water from the Pacific Ocean are targeted for extraction deep into the mainland. Why is such a radical engineering intervention necessary? Rivers have run dry, and fertile farmland has cracked into red dust. This bold maneuver aims to counter the most persistent and devastating enemy California has ever faced. But this is just the beginning. Engineers construct massive desalination plants to process the intake flow. One can notice how the infrastructure spans the dried landscape. At first glance, the plan seems to be just about pumping volume, but in reality, it integrates advanced wastewater recycling technology. This process intends to bring a once-dead land back to life. But the geography presents a significant physical barrier. It is visible how water pipelines stretch for hundreds of kilometers across the West Coast. The system quietly powers this ambitious solution with constant pressure. Transition to the next level of distribution follows. Because of this, the greatest water crisis meets a calculated technical response. 3.5 trillion United States dollars. That is the value of California's economy, ranking it as the world's fifth largest. Why does such a wealthy region struggle with a fundamental lack of moisture? At first glance, the state seems agriculturally robust, producing 1/3 of the nation's vegetables and 2/3 of its fruits. But in reality, this agricultural giant consumes nearly 80% of all human-used water in the state. Geographically, the land sits wedged between the cold Pacific Ocean and the towering Sierra Nevada. This natural wall blocks most of the ocean's moisture from reaching the interior. Most rainfall lands in the north, while the south endures a semi-desert climate. One can notice how the snowpack accumulates on the peaks, creating a massive water bank that provides over 60% of the natural supply. But this cycle is collapsing. Snowfall has dropped by 20 to 60% in drought years and melts weeks earlier. It gets more complex further on, but the state is now in its worst drought in 1,200 years. Major reservoirs like Shasta, Oroville, and Meade have fallen to just 40% capacity, revealing dry earth along the banks. Americans could not simply wait for mountain water to arrive. Instead, they turned to a nearly endless source, even though seawater contains 3.5% salt. Giant desalination plants were built along the Pacific coast to handle this task. Every day, this plant converts 7 million liters of seawater into drinking water. The system uses significant energy to complete the process in just 90 minutes. The treated water quietly flows into the distribution network. 15 million liters per day is the volume of raw seawater a single intake pipe draws into the system to begin the desalination process. To handle such a massive continuous flow, engineers installed gigantic intake pipelines made of carbon steel or large-diameter high-density polyethylene, often measuring 2 to 3 meters across. Each individual pipe section stretches for dozens of meters and must be lowered into place using heavy lift cranes, creating a structure built to withstand salt corrosion, crushing water pressure, and the relentless impacts from ocean waves. One can notice how the segments are connected piece by piece with high-pressure gaskets and fully sealed welds to prevent even the smallest leak. Finally, the entire pipeline assembly is secured with heavy steel frames and seabed anchors to keep it stable against strong underwater currents in the harsh coastal environment. Why are the intake points positioned hundreds of meters offshore? It would seem easier to simply draw water directly from the coastline, where infrastructure is closer. But barriers and intake filters placed at this specific distance effectively catch large floating debris and prevent marine life from entering the high-velocity flow. A pipe with a diameter of just 63 centimeters pulls in water at a rate of over 10,000 liters per minute. Powerful pumps drive this immense volume toward the plant. As the seawater is drawn in, uninvited guests like jellyfish, crabs, and occasional small fish are inevitably pulled toward the current. To prevent them from clogging the delicate machinery, a massive screen blocks anything larger than 4.5 millimeters in diameter. The water then passes through finer screens to filter out the remaining large particles, but the process is only gaining momentum. Even after the larger organisms have been removed, the fluid is still full of suspended sediment that could destroy the system. The solution involves a process called filtration inside large tanks, where water flows downward through layers of specialized sand using gravity. One can notice how the sand continuously moves downward, opposite the direction of the water flow, trapping dirty particles on the surface of the grains. The gaps between the sand grains are so small that only water passes through, while suspended matter clings to the medium. This filtration removes anything larger than roughly 1/10 the thickness of a human hair. Large paddles rotate ceaselessly in the mixing tanks, stirring the water as the plant introduces two critical chemicals: sodium hypochlorite as a disinfectant and ferric chloride as a coagulant. The coagulant forces fine sand and waste particles to clump together into larger flocks, which then settle at the bottom of the tank due to gravity. Most visible dirt is removed at this stage, yet the fluid is not yet ready for the main event. At first glance, the water now seems perfectly transparent, but in reality, it still carries microscopic threats that can damage the sensitive membranes ahead. Therefore, the water enters the cartridge filtration system, which serves as the final line of defense before reverse osmosis. Inside each housing, multiple cartridges made of tightly compressed fiber layers operate with pore sizes as small as 1 to 5 microns. The water flows from the outside toward the center of each unit, trapping microscopic particles between the dense fiber layers while clean water passes through the cartridge wall. Once a cartridge becomes saturated with debris, engineers manually remove and replace it to ensure the system maintains maximum efficiency. The seawater then moves to the most critical stage, separating the salt from the water molecules. Salt ions cling tightly to water through strong electrostatic attraction, creating a bond that is extremely difficult to break. To overcome this, the system must apply pressure greater than the natural osmotic pressure, forcing water through an ultrafine reverse osmosis membrane, while salt and other impurities are left behind. To generate this immense force, the plant utilizes high-powered centrifugal pumps. Each component of the pumping system controls a specific pressure stage, gradually increasing the intensity as the fluid moves through successive compression phases. By the time the water exits the final stage of the pump assembly, the pressure reaches about 60 bar. This is roughly 60 times atmospheric pressure, a force strong enough to separate water from salt at the molecular level. It gets more complex further on. After the first round of reverse osmosis filtration, the water is already almost salt-free, but it still contains trace ions and microminerals that must be completely removed to meet strict drinking water standards. Consequently, the water is sent through a second reverse osmosis stage where even finer membranes operate under lower pressure to achieve higher salt removal efficiency. This stage reduces the water's electrical conductivity to extremely low levels, stripping out the remaining ions and bringing the liquid to a true, purified water quality. The final result is an ultra-clean stream of water with near-perfect purity, ready for remineralization or distribution. However, after passing through the reverse osmosis membranes, the water's pH still needs to be balanced before humans can safely drink it. To do this, the plant adjusts the pH, usually by adding a small amount of acid or a balancing solution to bring the water back into a safe range. Desalinated water also contains far fewer essential minerals than typical drinking water, so to improve taste and overall quality, a small amount of minerals like calcium and magnesium is added during the remineralization process. This step restores the water's mineral profile, adjusts the pH, increases alkalinity, and brings back a natural taste, creating water that is not only safe, but also healthier and more pleasant for people to drink. The clean water is then carried through high-pressure pipelines to massive storage tanks within the plant, where it awaits use. From there, the water is pumped into the municipal supply network or delivered to drought-stricken agricultural regions. Although it is considered a technology of the future, desalinated water is relatively expensive, often costing 2 to 4 times more than conventional water depending on location and operating costs. Thus, the processed water completes its journey, ready for consumption. 700 kilometers, exactly the distance the California Aqueduct stretches to reshape the destiny of an otherwise dry region. The state did not stop at building coastal desalination plants alone, launching one of the most ambitious infrastructure projects in history. It all begins in the Sierra Nevada, where winter snow piles up meters deep on the rocky peaks. When summer arrives, this white blanket melts, producing a precious flow of fresh water that would otherwise rush aimlessly out to the sea. Why intervene with such colossal barriers instead of letting the river run its course? Nature seems to handle the flow well enough on its own. Engineers built massive dams like Shasta, Oroville, and Folsom to capture this runoff before it is lost. These structures create a reservoir system with a combined capacity of tens of billions of cubic meters, acting as water banks that protect California through every drought cycle. But the journey of the water is only gaining momentum. From these reservoirs, the flow is carried south through the Central Valley Project and the State Water Project. The backbone is the artificial waterway that cuts through valleys, crosses scorching deserts, and climbs mountain ranges. In places where the terrain rises sharply, giant pumping stations push water more than 600 meters up the Tehachapi Mountains. One can notice how the massive reinforced concrete pipelines scale the steep slopes, defying gravity with the power of immense turbines. At first glance, the water flowing through the open canal seems free, but in reality, delivering each cubic meter to end users comes at a steep cost. Tens of billions of dollars went into construction, plus billions more are spent each year for electricity and maintenance. Many areas have had to raise prices for both household and agricultural water just to keep the intricate system running. And this is not the limit. The existing infrastructure is now opening up a new future by seamlessly connecting with coastal desalination plants. This allows California to blend multiple water sources, combining water from the mountains with water from the sea within the same network. Thanks to this vast web of dams and aqueducts, millions of hectares of farmland in the Central Valley now have a stable, year-round source of irrigation water. This region supplies more than 1/3 of America's vegetables and 2/3 of its fruits. Fields that once depended entirely on unpredictable snowmelt can now maintain production even during severe droughts, turning the state into a global agricultural hub. Despite the high cost, this system remains the foundation that allows life to thrive in an arid climate. Thousands of cubic meters of wastewater converge deep beneath the city every single day. This immense flow from toilets, sinks, and even industrial facilities travels through a vast network of underground sewers. It arrives at the treatment plant carrying an unpredictable mix of shredded paper, plastic bags, wooden branches, sand, gravel, and grease. California has built these massive recycling plants to ensure that not a single drop goes to waste in an otherwise arid climate. Alongside seawater and natural freshwater sources, these facilities supply clean water for agriculture and cities, while reducing pollution in rivers, lakes, and the ocean. Why does the treatment process begin with a row of stainless steel bar screens? The flow seems liquid enough to pass through pipes. But without these mechanical gatekeepers, the rigid plastics and scraps of fabric would clog the delicate downstream machinery instantly. These grids trap large debris, so the flow remains unobstructed, but this is just the beginning. At first glance, the enormous settling tanks seem to be simple holding pools, but in reality, they function as a precise gravitational separator. The water passes through grit chambers and enters these rectangular or circular structures, capable of holding thousands of cubic meters. One can notice how the velocity of the flow slows dramatically within the basin. As the movement ceases, heavier organic particles, including fecal matter and food residues, sink to the bottom to form a dense layer of primary sludge. Meanwhile, mechanical skimmers move continuously in a circular motion on the surface, collecting floating grease to leave a clear middle layer. Because of this separation, the sedimentation tank serves as the first line of defense, yet the process is only gaining momentum. The water enters the decisive phase of biological treatment inside massive concrete basins several meters deep. Thousands of fine air diffusers at the bottom release a storm of tiny bubbles. It is visible how the rising air stirs the entire water column, delivering a steady supply of oxygen. Billions of aerobic microorganisms come to life in this rich environment, tirelessly consuming and breaking down the remaining organic compounds day and night. Activated sludge begins to form clusters known as flocks, binding countless microscopic particles suspended in the fluid. Therefore, even though water leaving the secondary settling tanks appears clear, it still holds microorganisms far too small for the human eye to detect. To eliminate them, the flow enters massive filtration chambers, where layers of dark membranes function as an ultrafine gateway. This microfiltration system blocks bacteria, parasites, and the tiniest suspended solids with absolute precision. Transition to the next level. The stream is pumped under tremendous pressure into rows of white cylindrical tubes. These reverse osmosis modules act as the very heart of the entire system. Inside each tube, multiple layers of semi-permeable membranes are tightly wound, with pores hundreds of times smaller than the width of a human hair. The pressure inside reaches tens of bars, driving a process that separates every molecule larger than water. One can notice the liquid exiting the cylinders, finally shimmering like liquid crystal. This marks the transformation of wastewater into a resource clean enough to drink. One ultimate goal dictates the process, ensuring the water is safe to drink. California's bold mission reclaims every drop of water for the future. Why are engineering marvels necessary here? Traditional supplies are shrinking rapidly. These technologies are reshaping our world to compensate for the deficit. The effort gains momentum. At first glance, purification seems routine, but in reality, it is a critical survival strategy. One can notice the sheer scale of the infrastructure required. Reputable sources confirm the reliability of the system. The technology advances steadily. It gets more complex further on. New methods ensure the liquid is pure. This completes the current reclamation loop. Thus, the water flows toward its destination without haste.